My name is Kaden Korn, and this is my video for Lab 2 for Physics 2211, which is the motion of a falling object. So, first of all, let's go over the purpose of the experiment. We're going to be comparing the motion of a falling object with and without drag being incorporated. And so basically that means comparing theoretical motion and observed motion with and without drag. And we're going to do this using tracker and glow script. So first of all, there's some necessary information to be able to understand this lab. First of all, Newton's second law, A equals net force over mass. We often assume that the only force close to the surface of the Earth is gravity. However, there's external forces such as drag, which we'll be focusing on here. So as a preview, we're going to see that drag can cause the acceleration of an object to be less than that predicted by the force of gravity. So here's a diagram of the net force, a free body diagram. First of all, you have gravity going down here, and then we have, resisting that is drag, so likely there will be less acceleration and less net force when that's taken into consideration. The system is the paper ball, and the surroundings is gravity and drag, basically. So here we'll go over the basic experimental design. First of all, the goal. The goal of this lab is to measure the position of a falling object to make a predictive model with drag and the force of gravity. To do so, a few steps are laid out for this lab. First of all, we need to take a video of the path of motion of a falling paper ball from around 1 meter. And then using tracker, we'll analyze the ball's motion. And then using the data that we collect from that, we'll create a computational model of position versus time using only gravity, and then a second model using both gravity and drag. And then we'll compare these graphs and see the kinds of effects that drag has on the motion of a falling object. So the initial conditions for this experiment are as follows. First of all, we can use a paper ball because it experiences a force of gravity, but because of its shape and general lightweight, it'll experience a moderate amount of drag, which will make it easier to observe than a heavier, more sleek object. Also, we're going to assume that gravity and drag are the only forces acting on the object, which they should be the main forces. And 3, we're going to isolate the falling ball from any external factors such as wind, so we're avoiding, any open doors or vents or anything like that. So here we have the glow script model using just gravity. As you can see, it follows a perfect parabolic motion, which is as expected. This is what you would calculate using the basic kinematic equation and whatnot. And over here we have a preview of the code where we've put in the mass of the ball and adjusted various values, as you can see, so that the model is effective with just gravity. Now, here's a comparison of the experimental data using having only gravity and gravity in drag positions versus time. As you can see from here, the experimental position with drag should be more similar to real motion, but clearly it doesn't accelerate downward as fast. So the model without drag falls faster. So therefore position with drag has a lesser downward acceleration. This can be explained fairly simply. This is because the drag force is acting in an upward motion, which is opposite of that of gravity, and also that the force of gravity was still stronger than the drag since the object continued to accelerate downwards instead of being stationary or accelerating upwards. There are a few potential errors with this experiment. First of all, in tracker, the ball is released at t equals 0, whereas on glow script, the object is released after t equals 0. And basically, this has an impact on how the position models will line up with each graph because they'll be shifted. Now looking at which model depicts terminal velocity. First of all, terminal velocity is found when drag equals gravity, therefore net force is 0 and the velocity is constant. And none of these graphs show constant velocity, therefore terminal velocity is not reached, and this is likely because the object needs to fall a greater amount of time. Now to look at a hypothetical, if the object was thrown upward instead of downward, this would mean that the speed at the same point would be greater because it would experience the acceleration of from the upwards throw. And greater speed equals greater drag. This means that there would be more experienced drag, and terminal velocity would be reached faster than if it was just dropped. That's everything I have. Thank you so much for listening.